My name is Naveen Karki, and of course I'll be taking the physics part. As I said, that we'll be talking about units, measurement and dimensions. Today's agenda is that. And as I had said in the previous case, just to be more focused and more precise, we would be directly going into the numerical application. We would not be consuming much of time in the definition. Of course, wherever it is required, we would certainly do that. So to start with the dimension part, let us directly focus on calculating the dimension of electrical quantities. So let us see, first of all, let's try to find the dimension of capacitance, the regular one. What you do is that you also start solving it, and if you get the answer, you post the answer in the Telegram, either in terms of type or click the photo, crop it and send it. Now let's try to see, and just to save our time, because we'll be wasting 50% of time if I give the question and wait for the answer. Let's see, for capacitance, if you want to calculate the dimension, that is Q by V is the basic definition. It is not recommended you start with epsilon naught A by D, because then epsilon naught itself will be unknown. So Q by V, let's try to see. And this is equals to Q by potential is work done per unit charge, right? And you would be getting this as Q square divided by W. That's how it comes. The charge will have a dimension of AT, so it's been squared, so A square T square. The work done, if I want to find the dimension, that is ml square T minus 2. Now here I take the assumption that of some very basic quantities, you know how to calculate the dimension. Like for work done, it is force into distance, and you get that. So let's try to see what will be the overall dimension there. That's going to be m minus 1 L square T 4 A square. So that will be the dimension of capacitance. M minus 1 L minus 2, sorry, this goes upstairs. So M minus 1 L minus 2 T4 A square, that will be the dimension of capacitance. Initially at least we'll focus on maybe 3 or 4 quantities to calculate the dimension. And if you get the answer, if you solve it, it's better that you either put it or you crop your solution and you put that. But it is strongly recommended that you post your answer. So that was about the dimension of capacitance. Let us try to deal with one more electrical quantity, and that is the resistance. All right. So let's try to find the dimension of resistance. Straightforward one, which is potential difference divided by current, right? And again, potential difference can be written as work done per unit charge into current there. And work done, that is of course equals to ml square T minus 2, charge is AT, and the dimension of current is A. So let us try to see what am I going to get. This is going to give me ml square T minus 3 A minus 2. So that will be the dimensional formula for resistance. So the basic idea about all dimension calculation is that if the dimensional formula for any quantity is being asked, then all you need to do is that try to find the suitable relationship. That's a very straightforward one, right? Now this is another question for you now. Try to calculate the dimension of mutual inductance. Don't confuse it with M. Don't confuse with mass. M is the mutual inductance. Calculate the dimension. That means we are going towards the magnetic quantity, right? Okay, so to calculate the dimension of mutual inductance, you need to find a relationship where mutual inductance is involved. And apart from finding the relationship, you also need to calculate a very convenient relationship. I think you can relate mutual inductance with energy. And all of you know that energy can be written as m multiplied by I square. That will be the energy part. Because half Li square, so half can be easily removed, that has no business in dimension. And instead of L, I've replaced it by M, because by nature they are the same thing. And then the mutual inductance is going to be, let me write it as M dash, because we also commonly use M for mass, so not to confuse that. Energy, that is equal to ml square T minus. So let's see. So coming to the thermodynamic quantity. In thermodynamic quantity, we would be introducing two new fundamental. One is the number of moles. So number of moles will have a dimension of mu. Remember, number of mole is also a fundamental quantity. And the next is temperature. Temperature will have a dimension of theta, or many times we also represent it by K. K stands for Kelvin. So whichever way you are trained with, how you did in the previous one, you can continue with that. The number of mole and this one. Now based on this, let us try to find the dimension of universal. So yes, I was talking about the dimension of universal gas constant, and in case of universal gas constant, the dimension, if I want to calculate it, it's something like this: pressure into volume. That can be straightway written. You just be careful, this is temperature, so it's better you write it as T theta, because capital T we generally use for time as well, just to avoid confusion. So PV will be ml square T minus 2 divided by number of moles will be mu, and temperature, if we prefer to write it in terms of theta, so the dimension of R is going to be ml square T minus 2 mu minus 1 theta minus 1. So that's how we calculate the dimension of universal gas constant. See, the whole idea, I think calculating dimension, the viewpoint, you know it, that's not a difficulty. And one more for thermodynamic quantity. Just go for the calculation of Boltzmann's constant. Try out for the Boltzmann's constant. So that means you need to search an expression where Boltzmann's constant would be involved, and you need to find that. So try and find the dimension of Boltzmann's constant. Okay. So the dimension of Boltzmann's constant, if we want to calculate that dimension of Boltzmann's constant, energy equals to 3 by 2 K times temperature. Let us write it as T theta. And if I want to find K, let us say that is energy by temperature. And energy is of course ml square T minus of 2 and T theta, so that is theta minus of 1. So that will be the dimension of Boltzmann's constant. All right. Okay. So I hope with all these cases now you've got a fair idea how we calculate the dimension of quantities. And a little bit of announcement. If there is a technical issue, don't choke the group by unnecessary messages and smileys. These are not allowed. Once the technical problem is there, the people back end will figure it out. So just patiently you stay and you can utilize your time. These things don't happen frequently. It's an exceptional case. So next time onward, there should be no any other messages. Yes, you may put it. If there is an issue, then you may put it down, but no other messages to clog the traffic. Please don't do that. All right, now let's see. Once you calculate the value of dimension, let us try to see the application of dimension. And in terms of application of dimension, there are certain quantities like electrical trigonometric quantities, exponential quantities, logarithmic quantities. And how do we visualize their dimension? Let's try to see. If you have e raised to the power anything, e is the normal exponent, anything in the power of exponent is dimensionless. And not only that, the entire e is also dimensionless. So I think quite easy for exponent, right? That whatever comes in the power of e, that is dimensionless, and the entire number e raised to the power that, even that is dimensionless. Now this discussion is specifically valid for those who are not so much used to with exponent, log and trigonometric. It's a very simple thing. A little bit of understanding, that is all we require. Similarly, you talk of sine, cos, tan, anything, because what comes inside is the angle, so that will also be dimensionless. And likewise, the entire value of sine, that will also be dimensionless. And the same logic holds true for log. The base can be anything. We don't mind for that. It can be base e, it can be base 10, any given thing. And that, anything which comes inside, that is dimensionless. And this is also dimensionless. So that is how we come up with the idea, the dimensional formula of mathematical quantities. So with this idea, let us try to see the applications of the dimension. And the first application, I assume all of you know, principle of homogeneity. And that principle of homogeneity says that if quantities are added or subtracted, the result will also have the same dimension. Like whatever is the dimension, say x, this will also have x and this will also have x. And on top of that, you may add as many quantities, that really doesn't matter. Like say for instance, you add velocity 100 times, the result will also be a velocity, isn't it? So let's try to see application based on that. So the first question here I would be taking is something like this. Say P is the pressure, and that is P naught by alpha e raised to the power minus of alpha t. Unless I give that this variable represents this, you can't assume unless given. And let me tell what are the parameters involved. This P is pressure and this T is given as time. Only this much it has been given. P is the pressure, T is the time. And on the basis of this thing, we need to calculate the dimension of P naught, that is, we need to calculate the dimension of alpha, that is, we need to calculate. Give a try. The dimension of P naught, dimension of alpha. Meanwhile, I'll soon join you. So you start doing it. Ravi, I'll just attend to your question. Let me do that. All right. Okay, so here the dimension of alpha, if I want to find, the logic is very simple. Alpha t, that is dimensionless. So that means alpha must have a dimension of t inverse, because this is time, and if the power has to be dimensionless, so this must be t minus 1. So that part has been done. After that, we also know that this entire thing is not going to influence in terms of dimension. So let us keep it aside. Then comes P is the pressure. So that is force per unit area, isn't it? So ml T minus 2 divided by L square, that's going to be ml minus 1. And P naught, we need to calculate the dimension. Alpha from the previous one we have done, that is T minus 1. So straightforward. Now this is going to imply P naught is ml minus 1 T negative 3. So that will be the dimension of P naught. So hope so with all these things you would be getting an idea that this is how you'll be applying the principle of homogeneity, because this is pressure, so this also must be pressure. So we have certainly applied the principle of homogeneity. Good. So I've received answer from Chetna, and that is ml minus 1 T minus 3. Good, Chetna. That's very appreciable. So this is what I mean. If you would not be able to type, you can paste the photo, you can crop it, you can do that. That's good. Now there is a question here from Ravi. So Ravi says, if a quantity is dimensionless, does that imply that it is not a physical quantity? No, Ravi. We have lots of physical quantities which are dimensionless, like a common example, angle, that doesn't have dimension, strain, that doesn't have dimension, but they are certainly physical quantities. All right. So NE is there. Yes, NE. I told anything power of E is dimensionless. That's perfectly right. And not only the power of E, see, in case of E, the power is dimensionless. That's one fact. The entire thing is also dimensionless. So we have used the same property, that this is dimensionless, and that's what we have done. You're perfectly right, Annie Shrine. But next time I would really appreciate if you would stop posting these smileys in the group. Okay, Ravi says, what happens to the dimension when we differentiate it? We are coming to that. That's a nice thing. Now let us try to see dimensions when it comes to differentiation and integration. Let us try to understand that. To understand the dimension of derivative and integration, let's take a very simple example. Not simple, rather let us make something like this. d2x by dt square. Let's try to understand. Let's try to draw the example from already known parameter. d2x by dt square, that is acceleration. And the unit is meter per second square. So here you can now make a conclusion that this x will come as it is, and this is t square, so that will be t minus of 2. So whenever you have to write the dimension where derivative is involved, you got to do this thing. Like here, you could understand. Let us try to see one more example based on this. Suppose if I have to calculate the dimension of d3f divided by dx cube, where x is distance, position, and f is the force. So try out the dimensional formula for d3f by dx cube. Please try out that. What would be the dimensional formula? No problem, Annie Shrine. I'm so happy that you have really included this. So if I want to do that, d3f by dx cube, the basic idea, we had talked about this thing. See, the idea is very simple. F will come as it is. So that is ml t minus of 2 by x cube. That's going to be L3, right? And this is x cube, this is f. So this is going to be ml minus of 2 t minus of 2. So that's how we calculate the dimension where derivative is involved. And let us even give a hand where integration is involved. Let's try to see. For the integration part, say for example, I want to calculate the dimension of integral v dt. Now a little bit of idea, not much deviation. This dt is small time, infinitesimal time. But after all, it's time. Whether it's large or small, that doesn't matter. So dimension, it will have t. This v is velocity. And what about the snake integration? You know, this snake represents you are adding quantities. And adding a quantity 100 times, it doesn't matter. So here, this will not interfere in our dimension. So this v is lt minus 1, dt will be t. So this is lt minus 1. And this will have a dimension of L. So this is how we write the dimension wherever these sort of quantities are involved. All right. Thank you, Shubham Mathur. Thank you very much. Okay, ml minus 2, t minus 2. Great, great, Annie. That's very appreciable. Wonderful. Okay, after that, now let's try to go with other situation. There are some quantities, it's better, it's advisable that you keep those quantities in your mind. That will save your time for calculating the dimension. What are those? Let me just try to show. You know, and that is something like this. Say, for example, you have RC. You know, this is the type of question that has high probability to come in the examination. Because now, the examiner doesn't expect that you calculate the dimension of R, well, that's the original method. You do R separately, you do C separately, you do it. But be clever. Try to relate. All of you must be knowing that in case of an RC circuit, product of R and product of C is called as the time constant. So the dimension of RC will be straightway time. Right? So this is unbelievable, isn't it, if you hadn't realized it before. One is electrical quantity, other is electrostatic quantity, but the product is coming out to be time. And this is where you can save your valuable time in the examination. So why not we make a list, and we make a list something like this. What are the quantities that are involved in time? Let's try to see what are those quantities. All right, so the first one is say RC, that is time. Product of R and C, that is time. Next is also there L by R. Remember the time constant of RL circuit, right? L by R. Then the next is C. Just try to extend it. This is time, this is time. You multiply, that will be time square. So if you multiply that, LC is time square, but if you give a root, that will be time, because we are under the heading of time there. And this is also, you remember, for LC oscillating circuit, the frequency is 1 by root LC. That means the time would be root LC. Similarly, there is another quantity for time, which is rho times epsilon. Rho is the resistivity, epsilon is the permittivity. It's unbelievable. Try out later on. This will be the dimension of time. Now, this is strongly recommended that you keep these things in mind. Now, next, let's go. There is another one, and that is for velocity. So, let's see what are the quantities in velocity. The first one is this one, 1 by root of mu times epsilon. You must have been doing this, 1 by root permeability and permittivity, that gives us the velocity. There is also another term for velocity, which is E divided by B, the ratio of electric field to magnetic field, that is velocity. Okay? And velocity part is this much. You got time, you got velocity, there is energy. Now, energy would be ml square t minus 2. Where are you going to find energy? Like the first one, CV square. Recall, half CV square is energy. Similarly, you can find Li square. So n others you can relate, that is energy. There is another which is energy density. Okay, that's another one, the energy density. And what are the quantities in energy density? Let's try to see. The first one is B square by mu naught, epsilon naught E square. Not difficult. Recall, this is the magnetic energy density, this is the electric energy density. So, of course, you get B square by mu naught, epsilon naught E square, they are this. And next one, now that may be a bit unexpected to you because that's a bit unexplored. So, let me try to show that. The resistance. A very beautiful relationship exists for resistance, and let us see what are they. One relationship I can easily bring from here, say, this is time, this is time. If you equate them both, R square will be L by C, because time and time that can be equated. So resistance, one is root L by C. As I've already said, this is a bit unexplored, therefore keep this thing in mind. Root L by C, that's a dimension of resistance. Similarly, E divided by H is the electric field intensity. H is the magnetic field intensity. The ratio of E to H will also have the unit of ohm or the dimension ohm. So these are the quantities that you got to take care of. So hope that's not a problem there. Shubham, yes, let me come to the part. You wanted the integration. Certainly. For that, what we can do is, let me see, yes. Shubham, because the integration means addition. So that addition will never influence dimension, because you add any quantity 100 times, the dimension is going to be same. So next is V dt. V is the velocity, Lt minus 1. Dt is the small time. Whether the time is small or large, that doesn't matter. The dimension will be t. So the whole logic, Shubham Mathur, is all about integration means addition, and that will not be influencing the dimension. So guys, that was about the dimensional part. You know, rest other things, I'm pretty confident that you can explore it. Let's now go to the next thing. And the next thing that we talk about is the measurement science. In case of measurement science, I have found that students get a bit confused. So let us try to understand the concept related to measurement. First of all, there are two things. One is called as accuracy, the other is called as precision. And let me tell you, I've already said that we would not be focusing on the formal definition part because that's going to waste our quality time. But during the course of discussion, wherever you find anything to be noted, wherever you find anything to be, scribbled, do that immediately. So now let's try to understand. Let's consider the measurement part. In case of measurement, first value let me take, say a person is measuring acceleration due to gravity. And first person measures the value of acceleration due to gravity as 9.7 meter per second square. The second person measures acceleration due to gravity and gets 9.623 meter per second square. Now, how are we going to understand the accuracy part and the precision part? Remember people, accuracy means how close to the original value your measured value lies. And there is no suspense, acceleration due to gravity 9.8 meter per second square. So this value is closer to 9.8. So here you would see that is more accurate. So that's not a problem deciding. So how do you decide which is more accurate? The more proximity, more closeness to the original value, that thing is more accurate. But what you talk about precision, precision is talking about the fineness of the measurement. And that precision has a direct relation which are involved. I repeat again, precision has to be about the fineness. Now, in Hindi, how you call as किसी भी measurement की बारीकी, that how finely you measure. Like a millimeter scale is more precise than a centimeter scale. So how do you understand the fineness? This has 1 digit after decimal, while this has 3 digits after decimal. So this value is more precise. So here you would see that G2 is more precise. Well, we are comparing between 1 and 2. So the moral of this story is a reading which is more accurate may be less precise and vice versa. But it can also be a reading is more accurate and more precise. In other words, we cannot find or we cannot relate any direct relation that if it is more precise, it is more accurate or vice versa. Anything can happen. You need to see, you need to observe. And there is a very, formal science to measure the precision part, and that part is what you call as the significant figure. So now we will be making our understanding to significant figure. So let's try to understand what does this significant figure indicate. See, as I've already said, and the type of course we are doing it, we want to be as much efficient as possible. So we would not be, going into those areas of formal definitions and everything. I will not be discussing that how did the rules evolve. I would certainly be talking about what are the rules of counting significant figure. So, as I've already said, I will not be able to say that why is this considered significant, why isn't this considered significant, because as I've said, we are directly hitting the examination point. But yes, the idea is significant figure basically is the measure of least count. In other words, it is also the measure of precision. Lesser is the least count, more is the precision, and more would be the significant figure. Remember, lesser is the least count, more is the precision. A millimeter reading is more precise than a centimeter reading. So now we'll directly talk about the ways how we measure and how we count the number of significant digits. Let's start with that. And I would be giving examples. We would not be writing long sentences because we want to be as time efficient as possible. So the first thing is, see, rule number 1, suppose 4, 3, 2, 1, the total number of significant figures would be 4. If you wish, you may write it, all these non-zero digits, they are significant. Wherever the digits are non-zero, blindly it's significant. So therefore, while counting significant digits, non-zero is never a problem. The problem is with 0, because sometimes 0 is significant, sometimes 0 isn't significant. So to understand that, what will we do is that let us consider significant zeros, all right, and let us consider non-significant zeros. So if you understand the significant zeros and non-significant zeros, that's quite a simple thing. And this is how we are going to make our analysis more efficient. Let's try to understand the first thing. Where are the significant zeros? The first one is, say, 402 or 4.02. These are two different examples. the 0 is sandwiched between two non-zero. So in that condition, a sandwiched 0 will be significant, Okay, that's a first case. Now let's see, that's the first rule here. Wherever it is sandwiched and be their decimal, be not their decimal, that doesn't matter. If it is sandwiched, it is significant, and that even doesn't matter. Like you can have this 4.002. Now even in this case, this will be significant. So that doesn't matter how many zeros are there, but remember it should be sandwiched between two non-zeros. So this will have 3 significant digits, 3, and this will have altogether 4. That was about the first case. Now let's go about the second one. All right, now to consider the second one. This is the case. 402.00. That, just try to understand now. Look, this is sandwiched, significant, but these are trailing zeros. So I think I did not translate you what's the meaning of trailing, the final 0, but a very important condition, trailing zeros and in a number thing. Considering another example, let me show. In the same way, example 0.030200. Let's try to see. See, as of now, the rule, we don't know about this because so far we have talked about sandwiched 0 between two non-zeros, so we don't know. So no comment for this. But let's see, where can we make the comment? Non-zero, non-zero, significant. A sandwiched 0, significant. Trailing 0, significant. So the trailing zeros in a number with decimal, they will be significant. Now after that, let's try to go for non-significant. Let's try to see. In case of non-significant, this is the case. 40200. Now you need to understand. Let's try to see. Significant, because non-zero, non-zero, they are significant. 0 is sandwiched, so that is also significant. And what about this? These are the trailing zeros, but there is no decimal. That's not a decimal here. Oh, let me go with this example. We were, I suppose, 40200. All right, so let's try to see. That was a board sensitivity. Non-zero, non-zero, significant. Sandwiched, significant. This won't be significant. That means if there is trailing zeros but the number doesn't have decimal, that 0 will not be counted as significant. So just have a look. The trailing zeros with decimal will be significant. The trailing zeros without decimal won't be significant. And there is another case as well, and this is the case. 0.03020. Now let's see. Now just have a look. This is a number less than 1. All right. So for a number less than 1, anything will begin from 0. So these zeros, they aren't significant. Remember. So if a number is less than 1, so the initial zeros, they are never significant, but rest all non-zero, non-zero and sandwiched, and this is the trailing 0 with a number with decimal, so that will be significant. So this is how we deal with the zeros. We'll talk about others as well. Let me see if I got any message so far. All right, so now let's try to understand another situation. Let's try to see. So about the 0 part we have done. Hope so this will clarify everything. Just to go for a quick conclusion. More is to come in significant. But suppose if I have number like this, 2.003 4.30. So now just mentally calculate. We don't have time that you post the answer. It's a straightforward one. Non-zero, non-zero, that's going to be significant. The sandwiched zeros, they would be significant. And the trailing zero for a number with decimal, that's going to be significant. And I don't think so now you require more rule. For example, 40300, no decimal. So these zeros won't be significant. Rest, there would be 3 number of significant digits. Now, let's go with the next rule. And there's another beautiful rule for that. And what is it say? 4.300 into 10 raised to the power minus 6. Whenever you have any value written in this format. 4.300 into 10 raised to the power minus 6. Remember, we never consider this. So this is out of the picture. This is never treated for significant computation. And for the base, the same previous rule that you talked about, everything will be valid. So the trailing zero for a number with decimal, all are significant. So altogether, the total number of significant digits will be 4. So if you have anything in terms of exponent, this is how it goes. And finally, one small rule is there. Certain numbers which comes in formula, like perimeter of a square, of a rectangle, let's say, why to, take a square to make a special case. Perimeter of a rectangle twice into L plus B. This 2 comes out from the formula. It is not a measured quantity. Length is measured, breadth is measured, but 2 isn't measured. And this sort of number will have total infinite significant digit. All right. So whenever you get any value which comes out of formula, they will have infinite significant digit. Another example, if you want, for example, area equals to pi r square. This pi comes out from the formula. So this pi would also have infinite number of significant digits. So now, I believe there should be no trouble in counting and calculating the number of significant digits, right? So let's proceed now. To proceed further, we will talk about addition, subtraction, multiplication, division. Well, this is not to teach you addition, subtraction. In laboratory, how do we report the value? Now that's another thing, and very straightforward question. You don't require to put lots of effort, just by observation. A little bit of practice will do that. So let's try to see how are we going to go with the addition, subtraction. And the addition, subtraction will be included in the same rule. So let's see the addition and subtraction. Well, you would be getting something like this. Let's say 23.020 plus 0.01. And you have to choose the option that which is the correct answer for this plus this. See, the examiner is not expecting you about the additional skills. You know that. That's a basic assumption taken. But what is the rule? Let's say first. This is the case. Let's first add. That is 23.021. Is that what you find after you add this with this? But now, the main thing is, how are you going to report the answer? And trust me, out of 4 options, one option will be this, the correct one. Because I've already said, the motive isn't to check your additional skills. The motive is to check the rules pertaining to significant figures and other quantity. But here, be careful. Much have been talked about significant figure, so there may be a confusion. In addition, subtraction, we don't see the number of significant digits. We see the digits after decimal. I repeat again, while we go for addition, subtraction, we don't see the number of significant digits, we see the digits after decimal. This is 3, and here there are 2 digits after decimal. While as a matter of fact, if I count the significant figure, it's 1, isn't it? Now, the answer should have 2 digits after decimal. And why 2? The lesser one. So to go for 2 digits after decimal, you need to drop 1. So when you round off, that's going to be 23.02. That's what you get. And that is the correct option when you go for this. All right? 23.02. So you would be getting 4 options. All you need is that you need to tick. As I've already said, I will not be in the position to tell you, but there are logics, there are signs that why is this rule made, but let us not put our headache in that. Okay? So great. Mahalakshmi has said 23.03. That's great. That's great. I'll come to you, Shubham Mathur. In 4-3, there is a question from Shubham. In 4300 into 10 raised to the power minus 6, if we divide, we got 2 significant. No, Shubham Mathur, you mean to say a question this, 4300 into 10 raised to the power minus 6. If you want to count this significant digit, this is never eligible for counting, and the base will have the same previous rule. The trailing 0 won't be significant since the number doesn't have decimal. So this will be out of the game. It will have 2 significant digits. So Mr. Mathur, hope this will clear your doubt. Okay, Mahalakshmi, this is a name known to me. Were you with us in the first crash course? All right, now let's see. After this, let's try to understand the part. Okay, so addition and subtraction has been done. Now let's go for multiplication division. So multiplication and division. And what are we going to do in multiplication division? Let's see. I'll just take, okay, that's great. So I had a student previously by the same name. All right, now let's go for multiplication division. And for multiplication division, I can go in this way, like let's say 3.023 multiplied by 1.10, let us say. First of all, let's try to see how much will it be. 3.023 into. So the actual multiplication will be this much, 47.32530. So this is what you get when you actually multiply. But as I've already said, now in multiplication division, you know what are we going to do? In multiplication division, this is what you are going to do. This has 5 significant digits and this has 3 significant digits. So in multiplication division, guys, remember, we don't see the number after decimal. We see the least number of significant digits involved. So all you need to do is that you need to make it into 3 significant digits. So this much will be dropped. And since this is less than 5, so that's going to be 47.3. So that will be the correct answer. So it's, simple marks acquisition. You need not work out much. And remember, the topic measurement is important. So you got to be careful on that part. All right. So that was about the applications of this. Now we'll go to the next part. And the next part is, error and its propagation. So let's understand the theories corresponding to error and its propagation. See, the whole point is, you have any value, you measure any value in the laboratory, it always has a certain amount of error. The error may be minimized, but the error cannot be made 0. All right? Again, understand. The error may be minimized, but the error can't be made 0. I'll give you a very simple example. Suppose you have a centimeter scale. The error will be there within a range of centimeter. Now you decrease the scale further, the least count. Let's say from centimeter you go to millimeter. Now the error will be in millimeter. Further from millimeter you can go to micrometer, but the error would still be there in a micrometer because within the least count there is always an uncertainty. So if the whole idea is error is bound to occur, if error always creeps in, so why not to develop a formal mathematics which will study the error? So any value which is reported after being measured from the laboratory, it is reported in this way. MV is the measured value, and that measured value would be represented in this way. A plus minus delta A, where A is the value. And what is delta A called? Let's try to understand. This delta A is in fact the mean absolute error. All right. So that is called as the mean absolute error. So for instance, you are assigned a job to calculate the length of a certain rod. Then when you represent the rod length, you would be doing in this manner. A plus minus delta A. So plus minus delta A gives you the tolerance. The value can be anywhere between A minus delta A to A plus delta A. So this is the mean absolute error. There is another thing which is called as the fractional or relative error. So let's try to understand the fractional or relative error, and that is denoted by delta A divided by A. That's a fractional or relative error, and eventually the final one comes when you want the percentage error. So what is the percentage error? That's simply delta A by A multiplied by 100%. You multiply the relative error by 100, you would get the percentage error. So these are the basic terminology. After you understood the basic terminology, now let us try to see how will the propagation of error occur. Again guys, as I've already said, let us be more focused. Let us not go into the derivation part, and let's straightway see the error propagation part. The first is, let's talk about addition. So let's see how is error propagated whenever we are adding two quantities. And it is something like this. Say you are adding two quantities, Z equals to A plus B. Now remember, quantities are added and their corresponding errors would also be added. So we write in this way, if this, then what will happen? Delta Z will be plus minus delta A plus of delta B. This is what it goes. If two quantities are added, then the mean absolute errors of those quantities are also added to find the resultant. So that's straightforward in case of addition. Subtraction will surprise you if you haven't done it before. So let's see what is going to happen whenever we are subtracting two quantities. So it comes something like this. If Z equals to A minus of B, two quantities are being subtracted and there are individual errors in that case. So then you would find this. Delta Z will be plus minus delta A plus delta B. Here I would like to take your attention. Even if the quantities are subtracted, the mean absolute errors, they are added. I repeat again, the mean absolute errors are added whenever you subtract two quantities. All right, so why don't we have a numerical here? So let's try to see the example. Let's take, suppose there is a cylinder and the cylinder has outer radius 8.00 plus minus 0.01 centimeter. So that's the outer radius of the cylinder. And inner radius of the cylinder is, let's say, 6.00 plus minus 0.01 centimeter. So just imagine a cylinder having outer radius this much, inner radius this much. Now the question is something like this. You need to calculate the percentage error in thickness. Give a try. You need to calculate the percentage error in thickness. Give a try. Okay, so any shrine, I appreciate you have done it, but see, I've talked about the percentage error. Chetna says it is plus my 1%. Chetna, you're perfectly right. It's 1%. Yes. Disha, 1%. Great. All right, guys, so let me just show how are we getting that. Let me try to show it. And it's something like this, say. First of all, you need to talk about thickness. And what is thickness? Thickness is outer radius minus of inner radius. By definition, right? The outer radius minus inner radius, that is the thickness of a cylinder. So the quantities would be subtracted. So that will be 2.00. But we've recently seen the absolute error is added. So in that case, 0.01 plus minus that is going to be 0.02. So if someone asks, report thickness within its error limit, this is how you're going to report. And if someone asks, what is the mean absolute error in thickness, that would be 0.02. But the question wanted you to work out further. So it was not an easy deal. You got to calculate the percentage error in thickness. So that's delta T by T into 100%. That was required. So let's say that is plus of minus 0.02 divided by 2.00 into 100%. And that is not a tough task. So that is going to be plus minus 1%. So that will be the thickness within its error limit. Ravi, 1%, great. Yuva, 1%, wonderful, wonderful. All right, so this is what I had said in the beginning itself. The class has to be interactive, and never mind for the wrong answer even if you post, because you are in the learning phase. So I understand, therefore you have joined us. So there is absolute no problem to feel worried about. Just see if you get an answer, and if you calculate it, it's better, you report it. So that was about the thickness part. Now let's go to the next thing, and that is when quantities are multiplied. All right, so let us see what happens when quantities are multiplied. Say for a simple example, if Z is equal to A multiplied by B, two quantities are multiplied, then we get delta Z by Z is plus minus delta A by A plus delta B by B. Guys, remember, when quantities are multiplied, the relative errors are added. Quantity multiplied, I repeat, it's not the mean absolute error which is added. Now you got to remember, it's a relative error which is added. So this is when it comes to cases of multiplied. Now let's go for the next thing, and that is division. All right, so now let's try to understand what happens in division, and that's also again the same thing. When Z is A divided by B, then you find delta Z by Z will be equals to plus minus delta A by A plus delta B by B. That means, now if you can draw the sequence, if you can draw the pattern, like addition, subtraction has same pattern, multiplication, division, they have the same pattern, and that was valid even while you reported. Like remember, addition, subtraction, least number of digits after decimal. Multiplication, division, least number of significant figures involved in the calculation. So that's how it goes. So that's on a straightforward count for multiplication, division. We'll extend it, all right, a bit further. All right, now let's try to see. 10 minutes will extend. All right, now let's try to understand the next thing. Division, multiplication has happened, division has happened. Now let's try to understand when there's factors involved, like combined. Let's try to say with powers. For example, Z equals to A raised to the power M, B raised to the power N by C raised to the power P, let's say. Z is A raised to the power M, B raised to the power N by C raised to the power P. You know what? It comes as this. Delta Z by Z will be equals to plus minus M delta A by A plus N delta B by B plus P delta C by C. Did you realize the pattern? In fact, this includes both multiplication as well as division. This is what it includes. So this is delta Z by Z plus minus M delta A by A plus N delta. Now just see, imagine if there was no denominator there and M and N would be 1. This case will correspond to that of multiplication. Imagine there was no B and M and P was 1. This case would correspond to division. Now let me try to give you an example. For example, you have something, time period is 2 pi under root L by G. So what do you get? The fractional change is this, delta T by T is plus minus 1 by 2 delta L by L plus 1 by 2 delta G by G. This is how you get. Because the power of L and G both are half, and this guy, this is constant, so that will not be interfering in this calculation. So whenever there is a constant involved, that will not be interfering in the business. One more example if I would like to show, because specifically I have found many times students confused with this. Like, consider a volume of a sphere 4 by 3 pi r cube. So that's going to give you delta V by V is 3 delta R divided by R. This is what you get. And of course, with a plus minus sign, that's a part you'd be getting it. Right? But these are the regular featured question. Apart from this, sometimes, a bit of modified question comes, which doesn't come in this format. And objective examination is much about handling with the exceptional cases rather than going with the general. Of course, the idea of general is very much necessary. So now let's try to understand this part. To go with this, some special cases. So let's say one special case is this. 1 by R is 1 by R1 plus 1 by R2. That's a case when you are computing net resistance in parallel, isn't it? Well, I'll not be going for the derivation, but those who have a nice sense of differentiation can understand where is that come from. So you will get delta R by R square is delta R1 by R1 square plus delta R2 by R2 square. This is how it comes. And this is neither the fractional error nor the absolute error, nothing like that. But say suppose if I want to calculate the fractional error, so delta R by R is going to be delta R1 by R1 square plus delta R2 by R2 square multiplied by R. So be a bit tricky. Like if I wanted to calculate the fractional error, then delta R by R square, that R will go this side. This is how it happens, isn't it? So that's a case of when it's in parallel. Another example, suppose if people would ask me to calculate the mean absolute error, then the entire R square will be taken this side. So that's delta R. That means you can compute anything. You can calculate the mean absolute error, you can calculate the fractional error, any given thing. Another example, this comes here, is focal length computation. 1 by F is 1 by V plus minus 1 by U. So this will include both the case of lens, where there would be minus, the case of mirror, where there would be plus. So it will include both. In that case, what is going to happen is delta F by F square would be delta V by V square plus, you take your attention here, be it plus, be it minus. I think you can make a relation. Whether addition or subtraction, the pattern came same thing. So this also comes out to be the same given point. Alright, so this is how we make the special cases of 1 by F is 1 by V minus of 1 by plus minus 1 by U. The pattern is same thing. Okay. So now so we've done about this thing. We have talked about the error, we have talked about the propagation of the error, we have seen multiplication, division, and we saw the applications of dimensions and related to all given thing. Any point you have where there is a confusion, please say. Okay, so now let us try to see. We'll take 10 minutes further Now let's see, and we will talk about the situation of measuring devices, and that is vernier caliper. All right, so today we'll talk about vernier caliper, and next day we'll talk about the screw gauge. So let us see, how do we understand the vernier caliper part? So I hope all of you know what does vernier caliper mean like. So we'll be directly talking about this schematic diagram and everything. So let us try to understand about the vernier caliper, okay? Let's see. For the vernier caliper, it is something like this. I don't know how properly will I be able to make the figure, because least you can expect a nice figure from physics teacher, but let me try. Okay, now see here. This is a typical vernier caliper. Now just understand, it's quite an easy thing and it's important as well, remember. Now in case of vernier caliper, you have two scales. One is called as the main scale and other is called as the vernier scale. And this, you must be knowing that vernier scale can slide along the main scale, and this is the jaw of the main scale. So since we are completely into the schematic one, so the jaws are not going to affect us. So this is the main scale, this is the vernier scale. And you know, characteristic is there, the combined is called as the vernier caliper. So remember, main scale, vernier scale, and the combined will be called as the vernier caliper. Now let's try to see. First characteristic feature is, you know, that the vernier scale division is lesser than main scale division. I think you are comfortable with this. VSD, the vernier scale division, is lesser than the main scale division. And let me just try to show you the figure. It comes something like this. Like just imagine the main 0 is there, this is 1, this is 2, and so on, okay? And I'll show the vernier one. The vernier one would be 0 of vernier is there, 1 of vernier is there, 2 of vernier is there, and so forth. That must be clear, okay? So let's again see. The main scale is there, the vernier scale is there, and look at the characteristic feature that after, like say, in the first division, vernier is slightly behind the main. In the second, the gap further increases because little by little, the lag keeps on getting added up, and all those lag will finally make a larger one. Okay, so this is what happens, say. Like in the first, there is a lag, in the second, there is another lag, and in the later on, you would find something like this, say. Like suppose here, maybe this is the 9th main scale, and that will exactly match with the 10 vernier scale, and that is obvious, isn't it? Not necessarily 9 and 10, it could be 4 and 5, it could be 19 and 20, but that will happen. Like say for example, why does it match again? Let us take an example. Let us say the main scale, for example, not always, say the main scale is 1 millimeter and the vernier scale is 0.9 millimeter, just as an example. So what will happen? 9 division of main will be 9 millimeter, and the same 9 millimeter will be obtained in 10 division of vernier. Yes? So what happens is that initially when zeros and zeros are matching, you would have when again both the scales will match, the main scale will be one lesser than vernier. So that's very obvious. This is just for an example. As I've said, 1 millimeter 9 division is 9 millimeter, 0.9 millimeter 10 division would be 9 millimeter. So now let's try to understand it. Say it's something like this. Now we are coming to the derivation. If n vernier scale division, n for our case is 10, is equal to n minus 1 main scale division, like 10 vernier scale division matched with 9 main scale division. So you get the least count or the vernier constant. Remember, the least count or the vernier constant. Now just get used to with this. This is the vernier scale division. This is the main scale division. And least count of vernier constant is 1 MSD minus 1 VSD. 1 main scale division minus 1 vernier scale division, and that is also equals to 1 by n MSD. If you put it there, you get this much. So first, if you really, for those who had never discussed about vernier caliper, don't lose your heart. It's a very straightforward question you get. If you start practicing, you would certainly see, you can very easily do that. So this is the first one. Like, we'll take an example, okay? We'll take an example, don't worry. And it is something like this, say. Let me take an example. Let's say 1 MSD is 1 millimeter and 10 vernier scale division coincides with mean. Let's say. Suppose it's given that 1 main scale division is 1 millimeter and 10 vernier scale division coincides with mean. Now let's try to calculate the least count, and see, if you are lucky enough, you would get the question of least count itself. And majority of time, many times it has happened. And least count will be 1 MSD divided by n. 1 MSD is 1 millimeter, n is 10, so this is 0.1 millimeter. This is what happens. So that will be the least count of the device. I hope that is not a problem. As I have said, if that day is yours, direct question for least count you would get. But we would also see how the measurement is being done. Let's try to see. All right. Now refer to your practice book. You would see questions related to that. Now let's try to see the measurement part, how the measurement is done. So here, let me draw okay, so now let me show. The measurement part is also very simple. Suppose I wanted to measure the length of this object with high degree of precision. Suppose I want to do that. So in that given case, where is that object kept? The object is kept here. Here is that object. So this green color object is that object whose length you would like to find out. And you need to be careful with the measurement part. Say this is 15 main scale, this is 16, this is 17, say this is 18, this is 19, and so on. All right. And let us say the vernier division, let me try to show that. Here is the 0 of vernier, 1, 2, 3, and so on. So this is 1, 2, 3, 4 and so on. Now have a look very carefully. How do we do the readings? I wanted to find, this is the main scale, this is the vernier scale, and I wanted to find the reading of this scale, the length of the scale. And you know how are we going to do that? That length is going to be equals to, first of all, have a look. 0 of vernier is between 15 and 16. So that's going to be 15 main scale division. Why? The 0 of vernier is between 15 and 16. If 0 of vernier was between, say, 23rd and 24th main scale, so that will be 23 main scale division. Plus, there's a very, very important thing which you need to take care, and that important thing is this. You know what? Just have a look here. You would certainly find a point where a vernier scale will coincide with the main. Just see, the third vernier scale is coinciding with the main, the third one. So you are going to write in this way, plus 3 multiplied by least count. This is how it goes. So this is the whole technique, quite simple. As I've already said, those who had not done the vernier caliper calculation before, there's nothing to worry about. Very simply you can do. Why 15? Because the 0 of vernier is between or is after 15. And why 3? Because the third vernier scale matches with the main. And if I take the same previous scale where main scale was 1 millimeter and all, so this is going to be 15 into 1 millimeter, 1 main scale division, and the least count is 3 into 0.1 millimeter, the previous case what we had talked about, and this is going to be 15.3 millimeter will be the reading of this device. So that's how we calculate the reading of vernier caliper. All right. So today now we will be limiting this much, and tomorrow we'll be continuing a little bit of discussion about micrometers. Again, welcome all to the session there, and day by day you will get more used to start practicing. Thank you very much. Let me sign off. Take care. Bye-bye.